Okay, lecture 7. Should know the definitions of these terms. Now, it says determine the overall chemical equation for the following mechanism. So a mechanism is a set of steps that occur, a chain of reactions that occur at the molecular level that we don't normally get to see. They happen so quickly, but it's really what's happening. And what we get to see is the overall reaction. So first let's find the overall reaction. What you do is just add these up. You see you have two fluorine atoms. We don't normally see fluorine atoms because they're so reactive, but during a mechanism you get to see all kinds of unusual things that form because they only exist for a fraction of a second. That's what happens during a mechanism. And you know it's a mechanism first because I told you, but when you see these statements here, these designations, fast, slow, slow, you're talking about a mechanism. Notice there's no phases. Normally you don't put any phases like gas or liquid or solid into a mechanism because we're talking about individual molecules or atoms. Now once we've added them up, we get rid of the species that are the same on both sides. You can see that the chlorine is produced, the chlorine atom is produced, and then it's used up. The fluorines are produced here, and then they're used up. Those are intermediates. The things that are canceled are intermediates. So fluorine atom and chlorine atom are intermediates. Those are the ones that they're created during the mechanism, and they disappear, or they're used up during the mechanism. So on the laboratory scale, we never get to see them. They exist for a very, very, very short period of time, on the order of femtoseconds or picoseconds. And then they're gone. They're important. You can see that without them, we can't have this chain of reactions, but we just don't get to see them normally. So what we get to see is the overall reaction. Make sure I'm on the page. And this is something that looks very familiar now. Fluorine plus chlorine. So we put these gases together, maybe heat them up, put some energy in somehow. And we end up with chlorine monofluoride. So this is what we get to see in the lab, but this is really what's going on at the molecular level. Very quickly, a whole set of reactions are occurring right in a row that we don't normally get to see. Now you might say, well, if they happen so fast, why do we care? Well, a mechanism will often open up information about a reaction that we can then use for another reaction, a similar reaction. Give us some idea about the energetics of the system, some way of making the reaction go faster or slower, whatever we want it to do. So very important. You're going into organic chemistry, you're going to see a lot of mechanisms. So these are very basic compared to the ones you'll see in organic chemistry. Same thing here. When you see elementary reaction, that tells you you're dealing with a mechanism. But let's, the same thing. We need the same thing for this this problem, the overall reaction. Instead of writing them all out and canceling them, you can see we have atomic oxygen here as a product. It then goes on to become a reactant over here, gets used up. The SO3 is a product. It goes and becomes a reactant in the next step. So those are our two intermediates. Since they do cancel, no reason to bring them down, and just bring down the ones that don't cancel. And you know, if there's a lot of stuff, just bring it down, and if you forget to cancel something, you'll see it once it's brought down. This is the overall reaction, and so it is a so this kind of problem is very useful. First, that it shows us what's going on at the molecular level. But then we can also see that when we bring them together, we're back to a very common kind of reaction that you might see in the laboratory. Okay, so now 3. Here's another thing that we can do with these mechanisms is determine the molecularity. All we have to do is count up the number of species. 2 species are reacting together, that's bimolecular. 1 species is falling apart, unimolecular. 3 species are reacting together, termolecular, not trimolecular, termolecular. And it doesn't go beyond that. We don't do tetramolecular because having 4 species come together all at once in the same place doesn't often happen. You can have overall reactions that have 4 species or 6 species or 8 species, but they don't all react at once. They go in a series of steps. So if you ever see a reaction that has 4 species in it, you know that there's at least a couple of steps in the mechanism. It doesn't all happen at once. So just count up the species. If it's 1, it's unimolecular, 2, bimolecular, 3, termolecular. And that's all you have to do there. Now, because we can look at what is actually happening on the molecular level, we can write the rate law directly for each of these steps. Call this K1, K2. So we can write the rate law for this as the rate is equal to K1 times the concentration of O3 times NO2. And you say, well, you can't do that. You can't write it directly off a reaction. We learned that, but that's an overall reaction. When we're looking at the actual thing that's happening, these two, it's first order in ozone, first order in NO2. The overall reaction, we can see now, is hiding some information. But if we're looking at the mechanism, we're looking at the exact step, then we can write the rate law directly from it. And we can write the rate law for the fast step too. But what they want is the rate law for the overall. Now the slow step is often thousands or hundreds of thousands, even millions of times slower than the fast step. So even though the fast step does take a little time, the slow step is the thing that takes the majority of the time. So if you want to picture it on a macroscopic level, let's say that you take 5 seconds to do your part of a job on an assembly line, but then the next person takes 35 hours. Well, how long did it take? Well, it took about 35 hours. You could certainly add on your time that it took, but it's the slow person that really has dictated how slow the job will go, what the rate of production will be. So even though the fast step does take a little time, it's a slow step that really is the rate of the overall reaction. So we look at the mechanism, we find the slow step, we write it down. The K1 and K2 are just used to designate the different Ks for the different steps. Since they have different speeds, different rates, these two values have to be different. But now, since this rate of the slow step is the same as the overall, we can get rid of that 1 and just make it into a regular rate law that we've dealt with. So the bottom line is, when you're given a mechanism, there's going to be a slow step. The rate law for that slow step is also the rate law for the overall step. It's an approximation, but it is a fantastic one. We're not taking into account the rate of the fast step, but it doesn't matter because it happens so quickly. It's really going to be lost in the rounding. I mean, you could certainly do it. It would take a little extra work to do, but you'd find that it would never be important. So you're asked for the rate law. Go to the slow step, write the rate for it, and you can might as well get rid of that 1. It's a constant. We don't know what its value is, so make it look like a regular rate law. So let's try that here with this guy. Oh, we see it's a little different. We got this equilibrium going on. The reaction is going forward, and it's also going in the reverse. Should make this, and that might as well get used to this double arrow. We're going to be seeing lots of them. Those double arrows throughout the next, I think, 3 chapters. We're going to get into equilibrium a lot, so we're kind of jumping the gun here, but let's take a look at this. The rate law, as I said, should be the rate law for the slow step. Once we have it, then we could easily convert, get rid of that 2, and then that's the rate law. But notice, unlike the previous problem, NO3 is an intermediate. That is a problem, because we want to be able to study the species that are part of the rate law. Since NO3 doesn't occur in our overall reaction, it looks like we're in trouble. But when you see that fast equilibrium step, that tells you have an extra step to do. The previous one was a simple one. You just write the rate law for the slow step and you're done. If we look at it here, let me go back here. Note the rate law has ozone, which is part of the overall reaction, NO2, which is part of the overall reaction. That means this rate law can be used to study the overall reaction. But here, NO3 is not part of the overall reaction. Dang. So if our rate law is going to mean anything, if we're going to use it in the laboratory, we need to have a species in there that we can study. So it seems like, well, what do we do now? We can't deal with the fast step, but this equilibrium step, the rate forward in an equilibrium, and that's what an equilibrium means. The rate forward, so going in this direction, is the same as the rate in reverse. So if we write the rate fortunately I don't think I can fit everything on here. So looking at this reaction here, if we write the rate forward, this is going to be, so we'll just write it as this, K1 N2O5. The reverse rate is, and what we will learn in the next chapter is we treat the products as if they were reactants because the products are forming and going back this way. That's what happens during equilibrium. And every reaction has a reverse reaction. We just never talked about it before because most of the time it's unimportant. But now we're going to get into equilibrium and we need to know something about them. So we treat the products as if they were reactants and we end up with this rate. This is the tricky part for a lot of students, but we said at equilibrium these rates are equal, so these are equal. So set them equal. Now, the reason we did this is that if we can solve for NO3, which is a part of this rate law that we wanted to get rid of, then we'd have NO3 in terms of NO2 and N2O5, which are both parts of this reaction. So they can be studied. So what we do is we solve for NO3. We end up K1 N2O5, K minus 1 NO2. Then we have this NO3, and we're going to put it into this equation. So by substituting this term into that above equation, we end up with the rate is equal to K2, K1, K minus 1, N2O5, NO2, or NO, NO2. So we've taken this value, NO3, which we can't study, is equal to this term, which then we put into this rate law. We have this, and then we simplify. These constants, we don't know what their value is, so just call them K. And now we have a fairly complex rate law. We're not used to having a concentration on the bottom, but that's okay. It does happen. You should see some of the rate laws that people come up with. And now, but what we have now are 3 species that we can study in the lab. So let's take a look at this guy. Same thing. We have K1, K minus 1, a little, not quite as bad. Here's the overall reaction. And what we do is we write this is the slow step. So we write the rate law for the slow step. Now, if it was just ozone, that would be part of the reaction and we could stop. If it was that, we'd be done. But we have that atomic oxygen. That's an intermediate. It's not part of the reaction. So we look to the fast equilibrium step again. We know that the forward rate is equal to the reverse rate. And so that's K1 times the concentration of ozone is equal to K minus 1 times the concentration of O2 times the concentration of atomic oxygen. Solve for atomic oxygen because we're trying to get rid of it in our rate law because it is an intermediate. O3 and O2 are not intermediates. So we have that. Now we're going to plug this value into here. And what we end up with is rate K1, K minus 1, O3, O3, O2, which simplifies to K, O3, 2, and O2. And that's our rate law. I'm going to have to go back and listen to this video. This is actually I I think my 7th attempt at this lecture. Everything that could go wrong went wrong, so I'm so glad this is done. But everything is here, and so that should be it. That covers all of our mechanisms.